Hi, this is Chris Overholt, and in this screencast I'd like to show uh, FDS and Smokeview output quantities. I'd like to show the input file in FDS, how to specify various output quantities, and how to view them in Smokeview and in the output files that are generated by FDS. So what I've done first is I've modified the roomfire case. This is a case that comes with the FDS installation. So this input file was modified, just a few things. I changed the time of the simulation and also the grid resolution. I reduced it just to reduce the runtime. Other than that, you'll see the same geometry from the roomfire case. So if I open up the .smv file in Smokeview, there you see the roomfire case with a burner on a couch and various output quantities instrumented throughout. So throughout this screencast, I'm going to refer to this Smokeview window where I have the roomfire case open, and I'll refer to the input file where I've made some modifications and added output quantities, and I'll also refer to these CSV or comma separated value output files here in spreadsheet software. So I'm essentially going to be going through what's in the FDS user guide. So if you have that open, you'll be able to see more detail on the output quantities I'll go over today. So if we look in the latest version of the guide, in chapter 14, called output data, specifies the dump nameless group and various output file types and methods that you can use to visualize or get quantified output from FDS. So I'm going to go over devices, profiles, slice files, boundary files, isosurface files, and some other different output quantities. So if I switch over to the input file and scroll down about halfway here, I've started, and this is where I've made the modifications and added the output quantities that we'll be talking about here. So the first thing I want to start with is the dump line, and this is ampersand dump. Here I've added in frames equal to 300, and I just did that for convenience because I set the simulation time to 300 seconds up above here, time t end equals 300. So if I set in frames, that stands for number of frames that will be output by FDS for the various output quantities. So 300 seconds divided by 300 frames, I should get about 1 output frame per second. You can find other options for the dump name list in the FDS user guide. And I've had one more note here, that the ID parameter at the end of each output quantity is a name that will appear in the output file, and I'm referring to this ID parameter here, and you can set this to anything you like. I've just set it here for naming purposes or convenience, so that when we read the output files we can see what we're actually referring to. So we'll go ahead and get started. The first output quantity I want to look at are devices, and this is the DEVC name list. Devices are typically located at a single point in space, zero-dimensional. As we'll look at later, you can actually expand them to be spatially integrated or over a volume as well. So they can be 2- or 3-dimensional flows. But the simplest device has just an XYZ coordinate in 3D space, and these outputs appear in a file called roomfire_devc.csv. And so the first device I'm listing here has a quantity of temperature. It's located at x 2.6, y 2.3, and z 2.1. The quantity specified here in temperature, you can see a full list in the user guide. And so I have 6 temperature devices named temp 1, 2, 3, 4, 5, 6. And they're in the same x and y coordinates, but they have varying heights in the z coordinates. And so it's important to note that these temperature devices measure the gas phase temperature only, and we'll look at those in a second. Below that, I have thermocouple devices. So these lines are the same except that the quantity specified is thermocouple instead of temperature, and thermocouple devices act like a physical thermocouple bead, and they account for radiation losses and thermal lag as the bead heats up. So there will be a difference between the two. I've made a note that if you're comparing to experimental data, it's best to use a thermocouple quantity instead of temperature, because this will reflect corrections for the thermocouple. So if we go over to the folder where I have my FDS output files, if I view the DEVC or device.csv file, that should open up in a spreadsheet software, and this file contains all of the device output from that case, which I've already run. So you would see this at the end of the simulation. So this is 300 seconds of data, and here in the columns, the first one is FDS time, and the rest of them are the devices I have in my file. So the 6 temperature devices are here, and the 6 thermocouple devices are here. So if I plot, for instance, the temperature at temperature device 1, there you go, you see the temperature over time for that temperature device. So it looks like it goes up to about 600 degrees Celsius, it goes back down as the compartment becomes underventilated. And the same thing if I plot thermocouple 1. Actually, I'm going to control click these 2 columns so they're highlighted, and if I plot those two, I get the 2 lines. You see the blue line is the temperature device, red line is the thermocouple. See the thermocouple lags a little bit behind, and this reflects the thermal lag and also the radiation losses from the thermocouple. So that's how you could view those 2 devices. I should also note this output spreadsheet. I clicked all of the values and changed it to number earlier. That way it's a little bit easier to read than scientific notation, which is default. So if we continue on in the input file, going down here, you can specify other quantities. You can see the FDS user guide for a list of commonly used device quantities. And so if I open that up and go down here, you see 14.5 is a summary of frequently used output quantities. So if I click that, it gives some species that are common, but below that it gives a table, which is really helpful for seeing what you can output. On the very right column shows the file type. So D stands for device, I is isosurface, P stands for, let me just check up here, P stands for plot 3D, PA for particle, S for slice. So this table is a really nice summary of what you can output and how you can output it with a corresponding output quantity. So here I've listed radiative heat flux. It's also a point device located 2.6, 2.3, and 0.0. So it's about the middle of the room on the floor. IOR is a quantity we'll talk about in a second, but this will output the radiative heat flux at that point. So you can also place devices to measure solid surface quantities, and typically it's best to use the IOR option to specify the direction that the wall or the solid obstruction is facing. So here I have a quantity for wall temperature, and it also has an XYZ, so it's at 2.1, 0.0, 1.2. That is located, so this is the front of the model. If I spin it around, if I go to the middle of the wall in the X direction, middle of the wall in the Z direction, and I specify that Y00, it's that point there. And so I'm on the front wall, and I'm asking to output the quantity wall temperature. IOR is 2, and this orientation parameter is important for telling it which direction the wall is facing or the solid is facing. So in this case, this is my X dimension, this is my Y dimension, front to back of the room, and then the Z dimension is the vertical dimension. So this wall is facing towards the back of the room, which is the positive Y direction. So in that case, I've specified IOR is equal to 2. The other IORs are here accordingly. -1, 1, -2 and 2, -3 and 3 should be where the wall is facing. So here, if I go to the spreadsheet and go over to wall temperature here, if I plot that, I should be able to see the surface temperature of the wall at that point. So there we go, we have the wall heating up and reaching some steady state temperature after a few minutes. Also notice that the units are given at the top of each output quantity. So if I go back here, the last thing I want to show for devices is that you can actually also output integrated quantities over a planar or volumetric area. So the device I've listed here, you'll notice it's using an XB instead of an XYZ like before. And so I've specified this to be, I want to check the mass flow through the door. So that's represented by this green dot here, but it's actually a plane over this opening where the door is. And the way I've done that is from x4 to 4.9, y is 0, 0 because it's flat on the y plane, and 0 to 2 is the height of the door. I specified quantity mass flow, and what that does is if I go to my spreadsheet, I have kilograms per second. So this is an integrated mass flow over the doorway. So if I plot this quantity, I actually see negative values, which is okay because in this case it's actually flowing in the negative y direction. So it's flowing out of the door. So I have about negative 0.5 kilograms per second, and then as the flow stabilizes, this goes closer to 0. So that's a nice way to see mass flow, heat flow. There's various quantities you can look at that are devices, but they're integrated over a certain area. So if I continue on, I'd like to now look at profiles. Profiles are a nice way to look at what's going on in the solid phase calculations in FDS. So profiles output the time history of temperature within a solid obstruction. So the profile I'm showing here will output the temperature profile of the front wall at the point that I've specified in a separate file called roomfire_prof_01, and these are numbered according to how they appear in the input file. So this is the first one. So at 2.1, 0.01.2, which is also along the middle wall region here, the middle front wall, I want to see a profile of the solid phase gridding, and this lets me see the details of the one-dimensional heat transfer that's occurring into the wall. So if I go to my folder where my output files are, I see that PROF profile 01. So if I open that up, see again, I want to change this to number so I can read that a little bit easier. And so what I have here is I have a column of time, the number of points, and this is the number of grid points in the solid phase gridding. And then I have endpoints times depth, and then I have endpoints times value. So if I highlight all of these columns and plot them, I will see temperature profiles at various depths inside the wall. So this is nice to see, again, what the one-dimensional heat transfer calculation is doing, and you can get those specific points over time inside of the wall. So that was done with the profile, XYZ, and quantity temperature. Again, you notice I have to specify I should specify the IOR, and in this case it's in the positive Y direction, so that's 2. Now if you don't want a separate file for each profile output, you can actually also output the inner wall temperature of a solid as a device at some depth in the solid. This is output to the device file and not to a separate profile file. So there is one addition here. You'll notice the depth parameter, and that's the depth inside of the solid in meters. So this line actually looks a lot similar to this one, where I have XYZ, the middle of the front wall, quantity wall temperature IOR2,